Hello again, welcome to Magnetic Fields, video number 9, where we're going to look at the force on current carrying wires. Now remember in the last video we talked about how when a conductor carries a current it generates a magnetic field, and we learnt the right hand grip rule to work out the direction of those circular fields around a current carrying wire. And I did forget to say that the reason current carrying wires generate a magnetic field is because the electrons that are flowing, each electron has its own magnetic field because it's a charge rotating on its axis, and so it generates a north and a south pole and a magnetic field around it. And so when in a conductor all those electrons are flowing through it, it generates a magnetic field. So let's move on. So when a conductor that has an electric current is placed in a magnetic field, so a second magnetic field, you have an interaction between those magnetic fields and a force is a result. And the interaction of those magnetic fields, the field from the, let's say this is the current carrying wire, so the field there, and then if we had a horseshoe magnet there, we'd have two magnetic fields interacting, and the field lines coalesce into one field, with the resultant being that the wire experiences a force. And this equation is the one that controls that force. So this is a force due to the magnetic field, where, if we pop that in, newtons of course, this is the current that's in the conductor, this is the length of the conductor in meters, and this is the magnetic field strength. Now this is the angle that the wire makes to the magnetic field. 99.9% of the time that's going to be 90 degrees, and therefore it's going to be 0. No, 1. So if that's 1, we pretty much ignore it and we don't write it in. So the angle of the wire to the lines of magnetic flux, all the magnetic field lines. So here we have a horseshoe magnet and we're showing the magnetic field due to it. Here's the wire, and this time the current, we've got an arrow there, so the current is coming out of the page, and this is using the right hand grip rule. We get that shape, put the two together, and we get an effect like this. And although this isn't the best diagram, I think I'll have another one. The net result is the wire is forced this way, basically because there's more field lines over this side than there are that side. And the field lines are a representation of the field strength, and therefore it's pushing it away. So this is the same. Again, there's a permanent field. This is the field due to the current. Put the two together, and this is a better diagram. You can see that the field lines are now all on this side because on this side they're all going the same way, and this side there's a cancelling of the field lines, and that's why there's a lack of field there. And so the wire results in a force pushing it in the direction where there is a lack of magnetic field. And the current carrying wire has to cut the magnetic field. And so one way of thinking about cutting the magnetic field, let's say this pen represents the magnetic field and this big pen represents the conductor. If you can move and hear a clicking sound, it means it's cutting. On this diagram here, the current and the field lines are in the same direction, so there's no cutting, and therefore there's no interaction of the fields, and therefore there's no force. So you've got to be cutting field lines to have a force. Now we have what's now called, or we're going to introduce you to, the right hand motor rule. And this is one you've just got to remember. And basically you use your right hand, and it's called the motor rule because we've got a conductor carrying a current in a magnetic field. And that will contrast when we introduce the generator rule, which is in electromagnetic induction. But the motor rule, we must have a current, and so our thumb represents the direction of current. Now this is conventional current, so that's from positive to negative. The fingers represent the magnetic field, and therefore the palm shows you the direction that the current carrying wire will be pushed or experience a force. And so if we looked at a couple of these, there's our field lines. So we've got, oh, this pen's gone crazy today. If our field lines are going from north to south, boy, that's crazy. Okay, and so if we were to put our hand, and you can practice this, it's a good idea to practice. This mouse has gone all over the place. Using our right hand, our current is represented by I. If it's given as I, that's conventional current, and our palm fingers are pointing down, and so the wire is going to move in that direction. Let's get rid of all that dodgy writing. And in this case, another case similar, but it's going to swing out. In this case, it's got a pivot, so we should understand that. Let's just to confuse you, some books and web pages will use left-hand rule, and you're welcome to try using a left-hand rule if you want to. You've just got to memorize it, because you've got to sit in a test or an exam knowing what everything points at. And you can't confuse the hands because they have different meaning. You can try and do this. I don't know exactly how you manage to bend your fingers around like that, so I wouldn't recommend any of the ones on this page actually. Just stick to the right hand motor rule. Okay, and there'll be a video with the hand rules on the OneNote for you to have a look at. Now let's just do a bit of testing to see if we've learnt or remember our right hand rule. Remembering, our thumb is conventional current, our fingers are the field lines, and our palm will be the force. And that's basically a 3 axis at 90 degrees to each other, and it always has that arrangement no matter which configuration, so that's why we can always use our hand. So in this case we've got current coming out of the page. Okay, and this will and we've introduced a magnetic, so this would just be the field lines for the current out of the page. If we put a magnetic field B going down, you can see there's a lot of field lines over here, not many over there, so it experiences force. And if I was to do that, and you should do it to the screen, it's going to look a bit opposite for me doing it, but I'd line it up, go down, and then we want current coming out of the page, so I align myself like that when I'm looking at the screen. So you should be in a similar position, and that's why my palm is pointing to my right, because it says on the screen. So let's do some practice, and so it's a good idea we'll put these up and then have a go at them. I'll pause them and maybe pause the video, work out what the answer is, and then start it up and I'll give you the answer. So here, this is a tricky little one. Now this is interesting because although this is all conductor and all carrying a current, it's only the wire that's within the magnetic field that will experience the force. So we're only concerned about this section of the wire here. And so if we pause it, okay, arrange your hand, work out your hand, now pause it, okay, unpause it, now you didn't hear that, hopefully, and the answer should be force to the right. Okay, more practice. Now which way is this one going to move? Pause. Okay, have a go. Going to go up. So field lines across from north to south. So I'm looking at it, so I'm going to look the reverse to you. And current out of the page. So current into the page, sorry. So I've got to twist myself all like this. Force up. Next one. Okay, now the trick to this one is recognize that this is the positive. The current's going to go across here, across here, across here. So we've got to use our solenoid grip rule first off, and so that's going to tell us this is a north, that's a south. So the field lines are going from there to there. and it's coming into the page. So my prediction is down. Let's do another one. So similarly, pause it. Hopefully you got force going to the left. Okay, now here's a key. So into out of the page. Here's our question. So which way is this wire is going to move? So I arrange my hands like so. I would say into the page. Yes. Have a go at this one. What do you say? Which way do you think it's going to move? Oh, that's tricky. Into the page. Okay, I'm getting them right. Are you? So here we've got, now this is a dot, so it's coming out of the page. So point your thumb at you. All right, now my palm's pointing down, so it's going to be down or south. Okay, so what do you think is going to be this one? Pause it. Out of the page. What do you think this one is going to be? Okay, these dots represent the magnetic field, so the magnetic field is coming towards you. So pause. Alright, let's see. North. And what do you think this one's going to do? So I would pause it whilst you're thinking about it. East. And this one looks a little bit different, but it's just the same. It's just drawn a little bit differently. So try and work it out. Are you ready to pause it before I give you the answer? It's going to move southeast. So it's going to move down in that direction. And this one? So ready to pause it before I give you the answer? South. So now you can do questions 15, 16 and 17 in your booklet. And if you're any confused, just let's have a go at doing these in the classroom and I can walk you through it. So the next video is going to be the force between two parallel wires, which we did in the prac.